Another topic from which some objective questions are seen in GATE examination is the number of instantaneous centers of a 4-bar chain or any mechanism in general. So, if a mechanism is having n number of links, then we can derive the number of instantaneous centers in the mechanism. So, the 4-bar chain, I'll give you the example. Let's say we have a 4-bar chain like this. This is link 1, this is link 2, this is link 3 and 4. This is a fixed link. Link 1 is fixed. So here for every combination of links, we have one instantaneous center. So there will be, for example, there will be one instantaneous named I31, which is 3 respect to 1. There will be one instantaneous center I21, I24, I34, I14, I23. So these are all combinations possible. 3 1, 1 3 and 3 1 are same. Similarly, 1 2 and 2 1 are same. So these are all possible combinations. So how this, what is the meaning of different instantaneous centers? We will see in this diagram. I, for example, let's say I21. So that is instantaneous center of link 2, 1 2 or I21 is instantaneous center of link 2 with respect to link 1. So link 1 is fixed to the ground and 2 is rotating about this point A. So the instantaneous center of link 2 with respect to link 1 will be this point only, the A. So this will be I21 or I12. Instantaneous center of link 2 with respect to 1. Similarly, instantaneous center I41 is this one or 14. Center of 4 is 1. Then we have instantaneous center of link 3 with respect to 1. So 1 is a fixed link. So with respect to the ground, what is the instantaneous center about which the link 3 rotates? That will be I31 with respect to ground. So if you want to find that, you know the velocity of this point B will be perpendicular to the link 2. This will be perpendicular to link 4. You can draw a line perpendicular to these vectors and you can get the point I31. So this is instantaneous center of 3 with respect to ground, that is 1. And then again, whatever we left with I32 or 23, let's say. So that is a instantaneous center of 3 with respect to link 2. So this will be the point where 3 will rotate with respect to 2. This is I23. Similarly, this will be I34, where the link 4 will rotate with respect to 3 or the 3 will rotate with respect to 4. Then we have instantaneous center of 2 with respect to 4. So for constructing that, so that would mean I24 will mean that if link 4 is fixed, then how link 2 will rotate with respect to link 4. So this will be something similar that we saw for link 3 and 1 here. So when the link 1 is fixed, how the link 3 is rotating? For that, we draw perpendicular to the link 2 and link 4. We draw a line along with the velocities of these points B and C, that is perpendicular to link 2 and 4 respectively, and we found the point I31. Similarly, we can find a point to draw a perpendicular to the velocity of 2 along the. So in this case, the link 4 is fixed. If you want to determine I24, link 4 is fixed, so this will be rotating. The velocity is somewhere like this. So we draw a line parallel to link 3 and draw a line parallel to link 1. So these will intersect somewhere. That will be the point I24. So like this, you determine all of the instantaneous centers in the mechanism. Now these instantaneous centers are classified in different categories. One is fixed instantaneous center. So in this diagram, you will see since the link 1 is fixed, so I21 and I41, both of them are fixed instantaneous center. Second category is permanent instantaneous center. So these are permanent in their location, but they are moving. Okay. We know their location in the mechanism, but they are moving. They are not fixed. So these are of the kind this I23 and I34. We know that they will lie at the joint of 23 and joint of 34, but the position will keep changing in time. So I23 and I33. The third category is neither fixed nor permanent. In this category, you see I24, it is not lying on the mechanism, so it is not a permanent instantaneous center. The position with respect to mechanism will change, and also the position in space will also change. So we have two in this category, I24 and I31. Now, for the number of the question which is coming in the objective question is the number of instantaneous centers of for a mechanism. So if n is the number of links in a mechanism, then you have seen from this derivation that there will be one instantaneous center for each combination. So the number of instantaneous centers will be equal to combination possible of links. So and in the two at a time. So there will be I21, I14, two links at a time. The combinations possible. This will be NC2, N combination 2 is equal to N into N minus 1 divided by 2. So this formula just need to memorize. So in this case we saw the number of links were 4. So we found 1, 2, 3, 4, 5, 6 instantaneous centers. So in the case of 4 bar, you have 4 multiplied by 4 minus 1 divided by 2, that is equal to 4 into 3 by 2 equal to 6 instantaneous centers that we saw here. Now we'll illustrate the application of the velocity triangle and instantaneous center method for the slider crank mechanism. We draw the slider crank mechanism here. So this is the crank, this is link, this is R, theta with respect to horizontal, this is the piston, and this is the slider threading in a liner. So the velocity of the piston will, let's say, we term it Vp, velocity of piston, and the velocity of crank pin C, so it will be perpendicular to the crank, the direction is known, and we know the rotational velocity of the crank omega. So we know the velocity of point C, Vc will be equal to omega r. So for this link P, C, we know the velocity of point P, Vp, and velocity of point C, Vc. So we can find the instantaneous center. To find the instantaneous center, we have to draw a line perpendicular to Vp. So since Vp is parallel to PO, line connecting the piston to the crank center, so this line will be perpendicular to PO. And for Vc, since Vc is perpendicular to OC, that is crank, so line perpendicular to Vc will be parallel to crank. So we just have to extend the crank here in the straight line, and we'll get an intersection point. This is I. I is the instantaneous center. So in the case of slider crank, you know it's very it is line perpendicular to the horizontal axis passing through the piston. You can get the piston density. Now, if you extend this connecting rod along with VC can be different direction. Extend the connecting rod and draw a line perpendicular from O. You will find a point D. We saw earlier the application of point D, that if you multiply the net piston effort with OD, you will get the crank pin torque, the crank effort. So we will draw here. In this case, the triangle IPC and triangle CDO are similar. Okay. So one of the questions asked in examination is to find the angular velocity of connecting rod. So you know that from the identity that omega is the rotational angular velocity of link PC, that is constant for PC if you consider instantaneous center. So if Vp is the velocity of point P, then Vp divided by Ip will be omega, which will be same as Vc divided by Ic, and it will be same as velocity of C relative to P, or Vcp divided by Pc. So by any of these three, normally Vcp will not be known, Vc will be known omega r, so straightforward, and Ic you can draw the velocity, the instantaneous center triangle, and you can find the length Ic to determine omega velocity. In actual examination, you may not be able to draw the diagram, so you know that the trigonometrical relations for the slider crank mechanism are pretty much straightforward, that we have already derived. This is the angle theta, then this is angle beta. You can draw a perpendicular line, you can find this length, let's say L. So PL you can find, and LO you can find, and then you know this in the triangle IOB is a right angle triangle. So if you know the length PO, then you can find out that PO tan theta will be equal to IP. So like that you can find IP. You know the velocity of the piston from your earlier analytical derivation, and you can find the angular velocity of the connecting rod. We also observed that the triangle IPC and CDO are similar. You can make use of that property also to find it useful according to the problem to find the length IP. So get IP or IC from geometry and calculate omega. How the velocity triangle will look like for the slider crank? So for the velocity triangle, we have the point O is fixed. So all velocities are relative to O. We have fixed point O in the space, and then velocity of C with respect to O, Vc, we know the magnitude is omega r, and we know the direction that is perpendicular to OC, which is crank. You can draw the Vc, and Vp, we know that the direction of P is along the horizontal axis, so we can draw a line like this horizontal axis, and then the relative velocity of point C and P will be perpendicular to the connecting rod. So we'll draw a line perpendicular to the connecting rod, and we can get the point P. We will find Vp, and this is Vpc, velocity of P is equal to C, OCP. So we will find that triangle OCP, small letters, is velocity triangle. And the earlier principle for translation of velocity triangle, we see that it's pretty much straightforward to apply here. During the introduction of this section, we also told that the triangle of instantaneous center and velocity triangle are similar. So in this figure, triangle OPC is similar, all small letters, similar to triangle IBC, this was the instantaneous solution. You can also make use of this identity if it helps in the problem. Now we will take up some numerical examples in this subject of velocity diagram. So I'll take an example here. The example pertains to a slider crank mechanism. This is the piston, this is the crank center. Now the parameters given for this problem is R, that is crank radius, is 50 mm. Length of the connecting rod L is given as 200 mm. Crank angle at the position for which we want to do the analysis, theta. Theta is given as 40 degrees. L is R crank spin. And the crank revolves clockwise at a rotational RPM of 1000 RPM. We have to find omega. And the length of the center of gravity of the connecting rod is a point G. This is G here. That point lies 140 mm from the small end of it. This is the piston. This is crank P. G lies 140 mm. PG is equal to 140 mm. Now the question is to find velocity of piston, angular velocity of connecting rod, and the velocity and direction of velocity of point G, that is the instantaneous, that is the center of gravity of connecting rod. This is the problem solution, and we have to find this solution by instantaneous center method. This is also quite. So if you go on constructing the instantaneous center, we know that the velocity of point P will be in this direction along the horizontal axis along the point OP. So we have to draw a line perpendicular to OP first. We draw a line here like this, and then we know that the crank velocity will be perpendicular to the length OC. So it will be perpendicular like this, VC will be like this, and we have to draw a line perpendicular to that. So we have to just extend the crank in this direction. So they will go and intersect somewhere here. This point we will term as I. This diagram you have to draw to scale. So since you know you need a compass and a protractor and a scale for this, and since you know this theta is equal to 40 degree, you can draw a horizontal line, draw a line at 40 degree to that, cut it at C. C, you know the crank radius is 50 mm. You have to choose a scale for the diagram. Let's say you choose a scale of 10. So at 5 mm or 1 centimeter, you cut a line here. If you choose a scale of 5, and then you know from C the length CP, that is L, is equal to 200 mm. So from C, using compass, you cut the horizontal line, you get the point P, and then with the help of compass, you draw a perpendicular line here and extend this line to get the point I. So first thing is to draw the slider crank mechanism and the instantaneous center diagram to some scale. In this case, it is found that the scale of 2.5 will be good enough to do in an A4 sheet. So after we have to find out the velocity Vc. For finding Vc, we know it is equal to omega into r. First, you have to find omega. Omega is equal to 2 pi n, that is revolution speed by 60. Is 2 pi into 1000 by 60. This will come around 104572 radian per second clockwise. And R is given as 50 mm. So hence to 5236 millimeter per second. Now from the instantaneous center velocity diagram, we know that Vp by Ip is equal to Vc by Ic. So we use this identity, and that will be equal to omega Pc. That the angular velocity of the connecting equal to Vg by Ig. So all three quantities are derived from a single equation. So first we find omega Pc, the angular velocity of connecting rod. Pc, this is equal to Vc. Vc is given as 5236. Ic you can measure from this diagram. If you measure, you will find that Ic is equal to 103 in a scale of 2.5. Multiply with the scale factor for the diagram. If you draw, this will be equal to 20.33 radian per second. This is the answer of part 2, angular velocity of connecting rod. Now to find the velocity of piston Vp is equal to omega Pc into Ip from this equation. So 20.33 multiplied by Ip distance. Also, if you measure from this diagram, it is around 20, it will come around 20.33, and then the scale factor of 2.5. Simplifying, you will get a velocity of piston 4015.18 millimeter per second. Third part is to draw the velocity of get the velocity of point G here. So you know the point G lies 140 mm from P. Pg is equal to 140 mm. So draw point G 140 mm divided by the scale factor of 2.5. Then you connect the point G from our instantaneous center I using this line, and then you draw a line perpendicular to Ig. So this is the direction of velocity of G. This will be Vg, and Vg by Ig is equal to omega Pc from here. So Vg will be equal to omega Pc into Ig. Ig, if you measure from this diagram, it will be around 89. Omega Pc is 20.33 into 89 into scale factor of 2.5 for the diagram. So this will come around 4523.43 millimeter per second. We will take another example in topic of velocity diagram. This time we will take the example of a 4-bar chain. So a 4-bar chain is given like this in the problem. This is a fixed link. The length of link AB is 1.5 meter, BC is 3 meter, CD is 2.5 meter, and AD length is 4 meter. At a particular time instant, the link AB makes the angle of 60 degree with respect to link AD. It is provided that the link AB rotates clockwise at the RPM of 25 RPM. For this link, the problem given is determine first the angular velocity of link CD, and second angular velocity of link BC. So we'll go on solving this problem now by the method of instantaneous centers. So we know that the velocity of point B will be perpendicular to the link AB. So the line perpendicular to link this velocity of B will be an extension of line AB. We will draw that. And similarly, for the point C, the velocity will be perpendicular to link CD. VC will be perpendicular to CD. So we will draw a line perpendicular to VC, which is just the extension of the link CD. These two will intersect at a point will be called I. That is the instantaneous center of the link BC. So for finding the angular velocity of link BC, we know that the formula is omega BC is equal to VB divided by IB, the distance from the instantaneous center, that is IB, and VB is the linear velocity divided by the distance from the determining this, first we need to know VB and we need to construct the diagram. So the diagram can be constructed to a scale, and then you can measure the distances here, IB and IC. I'll give you the values straight away. So we draw a diagram, draw a line AD, make a 60-degree line and cut it at 1.5 meters to get your point B. And from simple geometrical construction, you can construct the diagram and extend the length AB and CD to get I. If you measure, you will get IC is equal to 3 meters and IB is equal to 4.65 meters. Now what about VB? VB is equal to angular velocity of link AB multiplied by the distance AB. Angular velocity of AB can be determined from the RPM, that is 2 pi into RPM is 25 divided by 60, 2 pi n by 60. So this is equal to 2.619 radian per second. Now with this, we can, with our problem is to determine omega BC. For that we need VB first. VB will be equal to angular velocity of link AB multiplied by length AB. Angular velocity of AB is found here as 2.619 and length AB is given as 1.5 meters. Now our problem is to calculate the value of omega BC, that is angular velocity of link BC. This is equal to VB by IB, 2.619 into 1.5 divided by IB. IB is 4.65 from the diagram construction. So to calculate this thing, it will come around 0.845 radian per second. This is the angular velocity of link BC. Now the next step is to find the angular velocity of link CD. So for that we need to find VC. Angular velocity of link CD will be equal to VC divided by the length CD, which is known. Because target is to find VC. From the instantaneous center velocity diagram, we know that omega BC is equal to VB by IB equal to VC by IC. So VC will be equal to omega BC multiplied by IC. So this value is equal to 0.845 that we have just calculated, multiplied by the length IC, which from the velocity diagram construction will get around 3 meters. And then omega CD is equal to VC by CD, so 8.845 multiplied by 3 divided by CD. CD is given in the problem 2.5. So this will come 1.014 radian per second. So this is the answer of the first part. So we have found the angular velocity of link CD.